Hello, and welcome to the General Physics Lab, lab number 9, which is going to be on basic circuit analysis. And actually, this is going to be your last lab that you have to do for a written lab report. And I will have some kind of second lab exam. Not sure exactly how I'm going to do it yet. I probably will do it through Brightspace, but it'll be some sort of online lab exam. I'll let you guys know the details when we get closer to that. Okay, so again, this lab is going to be on basic circuit analysis. And I'm sure by the time you do this lab, James will have gone over circuit analysis and lecture, so you have a good idea of all these concepts. But let me go over the basics right now. So I'm going to switch over to the lab handout. Okay, so let's start with a couple of definitions. So first of all, you can think of electric current as being the amount of charge that passes through a circuit element per time. So charge, which we usually denote by a Q, is measured in coulombs, and T, time obviously is going to be in seconds. So it's coulombs per second is the current. And a coulomb actually is a huge amount of charge. It's like the charge carried by around 6 times 10 to the 18th electron. So that's 6 with 18 zeros after electron. So that's quite a large charge. That combination of coulombs per second, we give that a name, and you may have heard this name before. It's called an ampere or an amp. So current is measured in amps. Okay, so that's current, right? Amount of charge per time. The next definition is something called the voltage drop or electrical potential difference, or the potential, electrical potential. It has different names, or sometimes people just say voltage. You can think of it as the amount of work done per unit charge to drive the electric charge through the circuit. Okay, so it's work done by charge. And the unit of measure for the voltage that we use is going to be the volt. Okay, so we measure the voltage in volt. And the voltage source, if we were an in-class lab, it'd be a battery. And this entire lab I'm going to do as a simulation. So we'll be able to simulate a battery. So just think of the voltage source as a battery, right? It undergoes some like chemical process to separate the charges, and then that can be used to drive a current through a circuit. And then electrical resistance is basically the amount of resistance offered to the flow of the current, right, when it flows through a circuit element. And that is measured in something called ohms. So resistance is measured in ohms. Now, there's a law, it's an experimental law that holds pretty well, that relates the current to the voltage to the resistance. It's called Ohm's law. And it states that the current is equal to the voltage drop. So sometimes we use delta V, meaning the change in voltage across the battery. So this is like our voltage drop divided by the resistance. So I equals delta V over R. Or sometimes you may want to find the voltage drop given the current and the resistance, and you can just multiply those, right? So you could rearrange this formula. So you could also write it as delta V equals I times R. Graphically, Ohm's law can be shown to be a linear relationship. So if you look at this, this is a linear relationship, right? I is a function of the voltage drop, and the slope in this case would be 1 over R. So I show that in this graph here, right? So if I plot I versus voltage, so current versus voltage, then the slope is just going to be 1 over R, because I equals delta V over R. Now, ohmic devices are devices that obey Ohm's law. And there could be many things that have resistance, right? You could have light bulbs or different objects in the circuit. In our case today, we're just going to use resistors. Okay, so resistors are devices that obey Ohm's law. They provide resistance to the current through the circuit. And in a circuit diagram, they're represented by a sawtooth pattern. So if you see a sawtooth pattern, that just represents a resistor. The voltage drop, right, which in our case is going to be a battery, that's usually represented by two parallel lines, where the longer line is the positive side. It denotes like the positive terminal, and the shorter vertical line represents the negative side. So when you see that symbol with two vertical lines, or they could be horizontal, just two parallel lines with one longer and one smaller, that represents your voltage source, or your voltage drop, or your battery. Now, there's a common confusion regarding the direction that current travels through the circuit. Current, as you know, really consists of moving electrons, right? And since electrons carry negative charge, they're going to be repelled from the negative side of the battery, and you're going to be attracted to the positive side of the battery. So that would be the direction of the true current. Okay, so it's really the movement of electrons. So let me see if I have an example here. Okay, so here is an example, right, of a circuit. Here's my battery. Remember, the longer line is the positive side, shorter line is the negative side. So the true current would be the movement of electrons that would go from the negative side, be repelled from the negative side. They would go this way, counterclockwise around this circuit. But many years ago, and I think, actually, I believe this is Ben Franklin, just assumed that it was the positive charges that moved. So the conventional current is defined as the movement of positive charges, even though in reality we know that it's not, there's no positive charges that move, it's the electrons, the negative charges that move. But you can think of it as if it's positive charges moving in the opposite direction, and you still get exactly the same answers. So people tend to use the conventional current, and that's what we're going to use in this lab as well. So the conventional current, I'm going to go back to this circuit, is going to be from the positive side of the battery to the negative side. So it would be like current, and the I here represents the current right in this direction. It'd be like the current, in this case, moving clockwise around this circuit. Okay, I'm going to bring up the iPad and explain a little bit about simple circuits, and then the two circuits that we're going to be really interested in, something called a series circuit and a parallel circuit. Okay, so let me talk about a simple circuit first. So a simple circuit is just going to consist of a voltage source, like a battery, and a resistor. So you can think of it like this. Here's my battery. And then there's just going to be a single resistor. And then these are just, the lines are just wires, right, that connect the resistor to the battery. So this would be my voltage across the battery, or my voltage drop right across the battery. The resistor has some resistance value. I'll call that R. And if we use the conventional current, we can think of the current as going from positive to negative. So the current I is going in that direction. Okay, now the way to think about this, let's say I wanted to measure that current I, right, using Ohm's law. Well, if you think about the potential, let's look at two particular points. I'll look at this point right here on this side of the battery. Let's say it has some potential, say V1. And then on the other side, and that it could be 0, it doesn't matter, you can call it some value. And then this side, it has a potential V2. So in other words, let's say it's a 1.5 volt battery, right? 1.5 volt battery. Then if V1 is 0, then V2 would be 1.5, right? So that potential difference is equal to 1.5. Now, because these are just wires, right, that connect everything, we assume that the wires are really good conductors. They have very low resistance. That means that the potential, this V1, since it's not going to change much because there's almost no resistance in the wire, the potential will be V1 over here. And then this potential will be V2 over here. So you can see that the potential difference, or the voltage drop across the battery, is going to be the same as the voltage drop across the resistor when you have a simple circuit like this. So if we want to calculate the current, we can simply use Ohm's law, and we'll find that the current is going to be that total voltage drop, delta V, divided by that resistance value. And that will give you the current through that simple circuit. Okay, now a lot of what we're going to do in this lab, at least mathematically, is we're going to simplify a more complex circuit into a simple circuit so that we can calculate that current. Some people call this like a total current. And by total current, they mean the current, you can think of it as the current going through the battery. Okay, in this case, there's just one current going around, but think of it as the part of the current going through the battery, the total current. All right, so the first type of circuit that we're going to see is something called a series circuit. So what does that mean? It means that the two resistors, we're going to have two resistors, they're going to be in series with one another. So they're going to follow after one another. So let me draw this out. So it'll look something like this. This is our battery, right? I'll call this delta V total. So that's our voltage drop. Then we have, say, a resistor right there, and then maybe one right here. I can think of this as, I'll call this R1, resistor 1. I'll call this R2. And then the resistor has a voltage drop across that resistor. So I'll call that delta V1, and I'll call this delta V2. So delta V1 is the voltage drop across R1, and delta V2 is the voltage drop across R2. And then for the currents, remember the current that passes through the battery, this part we're going to think of as I total. So you can also think of this part as being I total. And then the current going through the first resistor, I'll call this I1. And the current going through the second resistor, so that current is, say, I2. Okay, so what's true about a series circuit? It turns out that since charge is conserved, the current must be exactly the same that flows through both of those resistors, right? So for a series circuit, it turns out that I1 is equal to I2 is equal to I total. The current stays the same. Right, there's just one current that goes through all those circuit elements. So the current remains the same. Now, what about the voltage drop? Well, it turns out that here at the battery, I'm gaining a certain amount of voltage. Say maybe, I went up plus 1.5 volts. And then there's a voltage drop across the first battery and a voltage drop across the second battery. So my potential would be back to whatever it was on this side of the battery, say like V1. Therefore, we can say that the voltage gained across the battery, so we went up by delta V, is equal to the voltage drop across the two resistors. Or another way of saying this, if we call the voltage gain across the battery positive and the voltage drop across the two resistors negative, we can say that the total voltage, if we sum all the voltages in any loop around that circuit, it has to sum to 0. Okay, so we could say that we have a voltage gain across the battery, then there's a drop across the first resistor, a drop across the second resistor, that has to equal 0, right? The sum of the voltages have to equal 0. That's one of Kirchhoff's laws. And then if I move the delta V1 and delta V2 to the other side, then I have delta V total equals delta V1 plus delta V2. Okay, now let's say we want to simplify this to a simple circuit so that we could calculate I total. We could use Ohm's law and calculate I total, right? Because it's very, very easy to do when we have a simple circuit to use Ohm's law. So the question is, how do I combine these two resistors that are in series to form one resistor, and I can stick that into my simple circuit? Well, for a series circuit, it turns out that to get a single resistor, R total, if the other two resistors are in series, I simply add their two resistance values together. So R total is going to be R1 plus R2. So then for the simple circuit now, I'd have delta V total. I would combine those two resistors into just a single resistor. So this would now be R total. And now I could calculate that current I total. I total is simply going to be delta V total divided by R total, right? I'm just using Ohm's law. Okay, so often that's what we do. We try and simplify the circuit into a simple circuit that we can just plug it into Ohm's law and calculate that current. Okay, the next type of circuit that we're going to study is something called a parallel circuit. So a parallel circuit looks like this. So this is delta V total. This would be, say, R1. And the voltage drop across it would be delta V1. This would be R2. And the voltage drop across it would be delta V2. The current traveling through this part of the circuit is I total. Or remember, this is also going to be I total. And then the current going through just that first resistor, I'll call I1, and the current going through the second resistor, I can call I2. Okay. By the way, another way that you can draw this parallel circuit, and you guys see why it's parallel. So those two resistors are in parallel with the voltage source, right, with the battery. So you could also draw it like this. These are just wires on top and on the bottom, so it doesn't matter. We can bend those wires. If you want, you could even do this. You could say, you could have all of the resistors in the battery coming from the same point. It means exactly the same thing. So that is exactly the same circuit that I just drew. Okay, it's just easier to kind of draw it as rectangles. All right, so what's true about this parallel circuit? So again, this is, and right on top, this is a parallel circuit. Okay, so one thing that's true is that the voltage drop across the battery and across each of those resistors is exactly the same. And again, I can think about it in terms of potentials. Like if this is the potential on this side of the battery, say V1, because this is just a wire, right? This is just a wire here, right? These are all just wires. There's no voltage drop across the wire. We're assuming it has very low resistance. So this is also V1, and this is also V1. They're all at the same potential is what we say. Then on the other side of the battery, I have a higher potential, right? Say V2. And since these are just wires, this is also V2. This is also V2, right? In fact, anywhere here would be V2. So if you look at that voltage drop, remember voltage drop is just V2 minus V1, right? The change in that potential. That's going to be the same across the battery and for each of those resistors. Okay, so that's the first important thing with a parallel circuit is the fact that delta V total is equal to delta V1 is equal to delta V2, right? The voltage drops are the same, or the potential differences are the same. Okay, the other thing that is important for a parallel circuit is if we look at one of these nodes, do it in blue here. So a node is like where the wires meet. So think of this as a node right here, which would correspond to this node right here. And it turns out because of conservation of charge again, whatever current goes into that node must equal the current leaving the node. So in this case, right, if I look at this blue node up here, then I have I total coming in and I have I1 and I2 coming out. So I total must equal I1 plus I2. Or the other way to think about it is if I can look at this node right here. Right, in this case, I have, remember, this is still I1 coming into it because that's the current that passed through R1. This would be I2. So now I have I1 plus I2. That's going to equal what's going out, but that's I total. So in both cases, I'm going to get the same equation. The fact that the current going in to a node has to equal the current going out of the node. So I total is equal to I1 plus I2. Okay, now let's say I wanted to calculate I total, right, using Ohm's law. Well, the easiest way to do that is if I can simplify this circuit into a simple circuit, then I can just apply Ohm's law directly. So the question is, how do I combine two resistors that are in parallel into a single total resistor, like one single resistor? So how do resistors combine in parallel? Well, it turns out in parallel, this relationship holds. The fact that 1 over R total has to equal 1 over the first resistance plus 1 over the second resistance. And now if you do a little bit of algebra, right, if I multiply both sides by the lowest common denominator, which is R total times R1 times R2, and I solve it for R total, I can rewrite this as R total is equal to R1 times R2 divided by R1 plus R2. And that's what we're going to use to find the total resistance if I have just two resistors in parallel. If you have more than two, then you have to use the first equation here, and you would just keep extending it, right? 1 over R total would equal 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 and so on. But if you have just two, it's much easier to just use this formula to rearrange it and solve it for R total. Okay, so again, this experiment is going to be done using a simulation, because obviously we can't build circuits at home, so we're going to use the simulation. The simulations are really, really well done, so I think this will be really good. So let me show you that next. Okay, so actually, before I do that, let's look at the handout again, at your lab handout. So again, this is going to be a simulation. It's called Circuit Construction Kit, DC, right, direct current virtual lab simulation. And here's the link to it. I also will put the link on Brightspace separately. So what I want you to do first, and I'll describe all of this as we go through it, but let's just look at the handout. Construct a simple circuit. Remember, that's just a battery and a single resistor, where the battery is going to be a 9-volt battery, right? So we have a 9-volt voltage drop. And the resistor is going to be a 10 ohm, and then later we're going to make it a 20 ohm, right? We're going to do this twice. Okay, so what I want you to do is construct this current, this circuit, and then we want to measure the voltage across the resistor and the current that's in the circuit. Now, how do you measure voltage and current? Again, this is more applicable to if we were actually doing this in class, but it'll be the same thing with the simulation. So let me just describe it right here. So when you measure voltage, right, we'd have some multimeter. It would be set up to measure voltage. And it turns out you want the multimeter to be in parallel with the circuit. So you have to measure the voltage across the resistor. So think of this as the positive side of the battery. This is the negative side of the battery. So current's going to flow this way. You could have a switch. I just drew a switch in here, right? So you turn the switch on, like complete the circuit. Current's going to flow. Conventionally, current will flow this way. Think of it as the flow of positive charge. So this is the positive side. This is the negative side. And if I measure across the resistor, that'll give me the voltage across the resistor. Now current, the multimeter has to become part of the circuit. So it's going to be in series with the circuit itself. So to measure current, you have to break the circuit. By breaking the circuit, I mean like remove a wire. Make sure the multimeter is set up to measure current. And now again, since this is the positive side, right, and this is a negative side, positively would go here, negative would go here. If you reverse them, you just get a negative here and just be the opposite. So in this case, positive, negative. And see now, as the current flows, it's going to go through the multimeter and then back into the circuit. So the multimeter itself becomes part of the circuit. Okay, so question 1 is going to be calculate the current through the circuit for both of those circuits using Ohm's law, and then compare the measured current, what you measured, to what you calculated by computing the percent experimental error. And since it's a simulation, you're probably going to get 0 or something very close to 0 here, right? Whereas if it was an in-class experiment, there might be some error there because the batteries are not perfect. There really is a little bit of resistance in the wires and so on. All right, so let me show you the simulation. Okay, so here's the simulation website. Again, you can click on, you can either download the simulation if you want to put it on your personal computer, or you can just use it through the web. So if I'll click on this, it'll load it. All right, so let me move this out of the way a little bit. So here are the items, the circuit elements that we want to put in. And in particular, of our interest, at least, are going to be the battery, the wire, and the resistor. You can just click, drag these. You can rotate them, right? Just using the mouse, moving them around. So let me put the battery there. By the way, you can also represent all these things either in sort of an idealized form like they are right now, like how they would look in real life, or if you want them in circuit diagram form, you can click on this right here, and it just gives you the actual diagram. So this would be, of course, a battery, right? Positive side, negative side. This would be a resistor, and then that would be a wire. It's up to you. You can use either one. It's fine. Okay, so to set the values of these elements, like the battery, just click on it. And then down here, we can input the voltage. So I wanted, what did I want? 9 volts, I believe. Okay, whatever it is. Actually, I'll just do an example. Let's say I did 12 volts. I won't do it exactly the same as what I asked you guys to do. So let's say 12 volts. And then the resistor, let's say it was 30 ohms I wanted. Okay, you guys want to use the values that I put in the lab handout. This is just an example. And then to connect them, you drag the wire, right? Drag to this part. And then I need one on this side, right? Connect it. And it, actually, as soon as you connect it, it'll show you the flow. It'll animate the flow of the electrons. And remember, this is like the true current, the flow of electrons. We really want the conventional current, so we can click up here. Conventional current would be the flow of, you can imagine it as if the positive charges flowed, right? That's conventionally how people think about it. Okay, so now how do I measure the voltage across the resistor here? Well, there's a voltmeter here, right? You can just grab it, click on it. Remember, this is the positive side of the battery. This is the negative side. So this would be the positive side. This would be the negative side of the volt across the resistor we want to measure. So I would just move the negative lead to there, the positive to there, and that gives me the voltage, okay? And of course, it should be the same as the battery, right? In this case, so it's a 12-volt battery, so we're getting 12 volts across that resistor. Right, so you want to do that for both of your resistors that you put in your circuit with the given values in the handout. Okay, then current. Well, how do we measure current? Well, that's where we're going to use what's called an ammeter. Right, so we have an ammeter. And here we want to disconnect one of the wires. So we need to break the circuit. So to do that, you just click on one part. There's a little icon here for the scissors. Click it, it'll separate it. I'll make a little room here. And then this ammeter becomes part of the circuit. And then that value, 0.40 amps, that's going to be the current flowing through the circuit. Okay, and again, you're going to measure that for both resistors that you put. So for both circuits that you create, both simple circuits that you create. Okay, let's go back to the handout for a second. Okay, so again, question 1 is fill in this table, right, with the measured voltage across each resistor, the measured current that you got from the ammeter, and then you want to calculate the current using Ohm's law, and then compute the percent experimental error. Compare the measured and the calculated current. You can use the calculated current as your accepted value, right? So when you compute the percent experimental error, remember you have to divide by the accepted. So in this case, divide by the calculated current. All right, so that's for the first part. Part 2 is you're going to construct a series circuit, and it's the circuit shown in your lab manual. So I'm gonna actually post a PDF of that experiment from your lab manual, so you'll have these 2 pictures, but you only need these 2 figures really. So actually, let me show you that right now. Okay, so this is the series circuit that you want to construct here. So here's the battery, right? Think of this, because we're going to need to know these labels later. This side of the battery is labeled A, so A is still over here. D would still be right here. So A, D. And then across this first resistor, R1 is going to be A, B. So one side is A, the other side is labeled B. And then across R2 is C, D. Because they're gonna ask for the voltage across AD, AB, and CD. So that's what they mean. The voltage across AD is the voltage across the battery. The voltage across AB is the voltage across your first resistor. and the voltage across CD is the voltage across your second resistor. Now, these A's here, A1, A2, A3, those are the amp meters, and those are the locations where you want to measure the current. So when it says measure I1, it's saying put your amp meter in this spot right here and measure the current through the amp meter at this location. That would be I1. Then you would connect the wire again, then take out this wire, put the amp meter in here. In this location, that will be I2, and in this location will be I3. Okay, so let me go back to, okay, so we're back at the handout. So you're going to construct that series circuit. Again, you're going to measure the voltage across the battery. Right? This is power supply, that they mean battery in this case. The voltage across the first resistor, so that was AB, and then the second resistor, CD. You can think of R1 here as being the 10 ohm resistor, and the R2 as being the 20 ohm resistor, right? Because we're going to use the same two resistors we had before, 10 ohm and 20 ohm. So R1 is 10, R2 is 20. I'll even type that in right now. So this is 10, and then this is 20. Okay, so let me show you how to set this up, and then I'll walk you through the question. Okay, so let me break the circuit here. Oop. Put this back for now. There's many ways you can do this. You probably want to do something like this, like maybe put your first resistor there. Maybe put the second one down here somewhere. And then maybe another wire that connects those two. So that would be the circuit, right? But make sure that your battery has the correct voltage. I believe it was 9 volts again. And then you want R1 to be 10 ohms and the other one to be 20 ohms, right? So then to measure the voltage, right? Remember, one of them was AD across the battery. So you go the voltmeter, this would be the negative side, this would be the positive side. Then you wanted to measure the voltage across AB, across the first resistor. So this would be positive, this would be negative, right? Now, if you reverse these, what would happen? You would just get a negative voltage. Okay, so it would still be the correct absolute value, but it'd be a negative voltage. So there. And across this one, this would be the negative side, and that would be the positive side. That would be, I guess, CD, delta V CD, or VCD. And then to measure the currents, remember, you want to measure the current here at this location, at this location, and this location. So you have to separate this, right? Cut it, maybe shrink this a little bit, and then grab your amp meter, stick it in the circuit, and then that would be I1, right? That would be at that first location, I1. Then you do the same thing here, I2, and then I3. Okay, so that'll give you all of the values that you need. Okay, so once you have all those values, what you can fill in the table, the first thing you want to do is you want to compute the total resistance. If we were to combine those two resistors in series, right, how do you combine them? And my hint is in here, right? Remember, you just simply add the resistance values together to find R total. And now you can think of it as a simple circuit, right? Once you combine the resistors together, and you can calculate I total, right, using Ohm's law. So what do we use as our voltage drop? Well, you would use the voltage across the battery, right? So VAD would be your total delta V, your delta V total. And then R total would be your resistance. So I would be delta V, or VAD, over R total. Okay, so that would be the calculated current. And then you also want to answer question 3. So for a series circuit, we know several things are true, right? You want to confirm all those things that we know to be true about series circuits. So first of all, is I1 equal to I2 equal to I3 equal to I total? Remember, the current should stay the same for a series circuit. So you want to verify that, right? Like whatever numbers you get, you could show, yes, I'm getting, 0.43 equals 0.43 equals 0.43 and so on. Does the voltage drop across the battery equal the sum of the voltage drops across the two resistors, VAB plus VCD? Does that, if you sum those together, do I get VAD? So use your values and hopefully that will be true. And then this is sort of almost the same question here. Another way of writing the voltage drop across AB is using Ohm's law. We can rearrange it and we can say that the delta V, the voltage drop, is the current times the resistance. So if I take my I total and then multiply by R1, because remember, I total is the same, the current's the same throughout the entire circuit. So this is like the current that goes through R1 times R1. That should be the voltage drop across the first resistor, plus the total current, or the current that goes through R2 times the resistance R2. That should be the voltage drop across the second resistor. And those two should add to the voltage drop across the battery. So you want to make sure that that equation is also true, right? Fill it in with values. Okay, then the third part, simulation experiment part 3, you're going to construct a parallel circuit. So this is figure 24-8 in your lab manual. So let me show you that. Okay, so that is this one right here. Okay, so in this case, right, we have the battery, and in terms of the labeling here, this is A, this is B. So VAB is the voltage across the battery. Then we have a resistor R1, right? That's going to be your 10 ohm resistor. So this is labeled C and then D, the 2 points on opposite sides of the resistor. And then in parallel with that is another resistor R2, and these are labeled E and F. And then you're going to be asked to measure the current at 4 different locations. So these are the 4 locations. So where these A's are, the ammeters are. So A1, you want to measure it here. A2 is like right after the right after the first resistor, but right before it reaches the node here. A3 is right after the second resistor. So you can think of A2 and A3 as being the currents that pass through R1 and R2. So this would be like, I guess we call it I2 in this case, I2 and I3. And then A4 is the current passing through this part of the circuit. Okay, so to construct this, let's go to the simulation. I'll help you guys construct this. So it's going to be something like this, right? Let me get rid of the ammeter for now. Let's see, cut that out. So I want one resistor like this. Oops. Something like that. And then maybe one like this. That would be the same, right? That would be a parallel circuit. So if I want to measure the voltage across the battery, right? Remember that was like AB and then CD and then EF. Then grab the voltmeter. This would be negative. This would be positive. What did I use? 12 volts? Yeah, so this should be 12 volts. It is. And actually, since these are in parallel, what should be true about the voltages? So if I measure across the first resistor, it should be the same, right? 12 volts, and this one should also be 12 volts. And you guys will have to use whatever, I think I left it at 9 volts, right? So you want to use 9 volts for your particular experiment. Then to measure the current at those 4 locations, remember the first one was right here, so I need to split this. I can connect this up again, and then I need to put the ammeter in there. So that would be the current I1 in this case, right? Then if I want to measure I2, that was a current going through here, the first resistor. So what you can do is you could split this, maybe do it this way, connect these two, right? Move it apart somehow, and then move this in like that. And then that would be the current going through that first resistor. Then do the same thing for I3, and then the same thing over here for I4, right? So you want to measure those 4 currents. And again, you guys are using 9 volts for your battery. R1 is going to be 10 ohms, and R2 is going to be 20 ohms. Okay, so now you want to fill in, right, with all those measurements, you want to fill in the table here. So you have your 4 currents, right, at those 4 locations. You have your 3 voltage drops. Remember, VAB is across the battery. VCD was across the first, the 10 ohm resistor. VEF was across the 20 ohm resistor. For R1, you can put 10 ohms. R2, you can put 20 ohms. Now, V total in this case, remember, V total is the voltage across the battery. So whatever you got for VAB, and these really should all be the same, right? Because it's a simulation, they're going to be exact. But whatever you got for VAB, you consider that to be your V total. That's going to be your total voltage drop across the battery. R total, you have to compute, right? So how do I combine 2 resistors that are in parallel to get a single resistor R total? That's when you have to use that equation. You can either use 1 over R total equals 1 over R1 plus 1 over R2, or if you rearrange it, you can use R total equals R1 times R2 over R1 plus R2. So it's the product divided by the sum, right? And that'll give you R total. So you want to compute that. So, and I have that here in question 4. So compute the total current in the circuit using Ohm's law. First, you need to find R total. For the voltage drop, again, use just VAB, but these should all be the same anyways. Should be 9 volts, right? And then when you divide that, that'll give you your total current through the circuit, right? And then fill in all these values. Okay, question 5 is compare the computed value of the total current to the measured value of the total current. So compare your computed I total, and for measured, well, remember the circuit, let me go back to, so remember the parallel circuit looks like this. And I total, we always said, was a current, you can think of it as a current that's going through the battery on this part of it. So really, the measured total current is either going to be I1 or, sorry, yeah, I1 or I4, right? Represented by the ammeter here, A1 and A4. So either I1 or I4. We could use either of those. In theory, they should be the same as our measured value of the total current. We're just going to choose to use I4, right? But with the simulation, you guys should get exactly the same. You may not have gotten exactly the same if we were doing this in lab itself. But with the simulation, these should be exactly the same. So we're just going to choose to use I4. Okay, but that should be the I total, right? That we got by measuring it. Okay, so you want to compare the computed value of the total current, so what you computed here using Ohm's law, right, from question 4, to what you measured. And again, for measurement, we're going to use what we got for I4. We're going to use this value that we measured for I4. And you want to compute them by computing a percent experimental error, and that's in this table right here. So this would be the computed I total, right? Think of that as your accepted value. And then I4 is your measured I total. So that's your experimental value. Compare them by computing the percent experimental error. Make sure you always show me all these calculations. And then question 6 is calculate the total current in the circuit as the sum of the measured values I2 and I3. Remember that I2 was the current going through the through the first resistor, right? And then I3 was the current going through the second resistor. And at a node, whatever current goes into that node must be going out. So in theory, if I add I2 plus I3, that should equal I total, which is either going to be I1 or I4, or just, again, going to use I4 to compare it to. So you want to sum your I2 and I3. We're going to call that the accepted value. And then again, compare that to the measured experimental value of I4. Compare them by computing a % experimental error. And because it's a simulation, you may get 0% here, or very close to 0%. Okay, so then once you've done that, there's one other thing that I want you to do. So I'm calling the simulation experiment part 4. I want you to construct a slightly more complicated circuit. And I'll show you this in a second. I'll get on the iPad and show you what I want you to do. And then I want you to calculate, I'll show you the circuit in a minute. I want you to calculate I1, I2, I3, I4, and then the voltage drops, delta V1, delta V2, delta V3, delta V4, using the techniques that you learned in physics lecture. So hopefully by the time you're watching this, James will have gone over a lot of circuit analysis and shown you all these techniques. So use the techniques you learned in physics lecture, and then measure, now design this circuit using the simulation and measure those 4 currents and the 4 voltage drops. And then how did your values, your calculated values, compared to your measured values? You don't have to do any % experimental errors. Just hopefully they're pretty close, right? So tell me like how they compared, how the measured values compared to the calculated values. All right, so let me show you the circuit that I want you guys to construct. Okay, so this is the circuit that I want you to construct for that last part of the lab. So your battery, you're going to make that an 18-volt battery. So you can think of it as delta V total. This is going to be 18 volts. Then you're going to have a resistor here. And then 3 resistors in parallel. So one there, one there. Oops, this should connect. And then one here. So this is going to be a 36. So you can think of this as R1. This will be a 36 ohm resistor. Then R2 will be a 3 ohm. R3 will be an 18 ohm. And then R4 will be a 9 ohm resistor. So this is going to be, the current going through the first resistor is going to be I1. And by the way, that's also I total, right? Because that's the same current that would go through the battery. The voltage drop across that resistor will be delta V1. Then the current going through the second resistor, so going through here, this is going to be I2. And the voltage drop across that resistor will be delta V2. Then the current going through here, the third resistor, is going to be I3. And then this voltage drop will be delta V3. And then the current going through there, that'll be I4. And then this voltage drop will be delta V4. So using the techniques that you learned in lecture with James, you're going to calculate, right, I1. So you're going to calculate I1, I2, I3, and I4. And then also, once you have those, then actually, once you have those, that's sort of the hard part, right, is getting all the currents. Then how do I find the voltage drops like delta V1? Well, that's just going to be I1 times R1, right? Then you just use I times R to get your delta V. So then calculate your 4 delta Vs. Then you want to construct this exact circuit in the simulation, right? Make sure you have all these correct values put in, and then perform those measurements. So measure I1. You can put the ammeter like, say right here if you want to measure it. That would be I1. Then I2, you could either put the ammeter here or you could put it after it. It doesn't matter. Same thing for I3, same thing for I4. And then the voltage drop is just across, right? So it'd be like red on this side, black on that side. Measure the voltage across each resistor. And then you're just going to qualitatively compare what you got theoretically, right? What you calculated and what you actually measured using the simulation. And they should be very, very close. There may be a little bit of round off error depending on how you round things. All right, great. So that's it for the final lab, lab 9. And again, when we get closer, I'll let you guys know what's going to happen with the second lab exam. There'll be some sort of second lab exam on the 3 labs with wave motion and sound, the geometric optics, right, reflection and refraction, and then circuit analysis. Great, thanks.